Good morning, everyone. I'm Christina from the class of 2023. Thank you for coming in person through Zoom today. And I'm going to talk about my research project, the feeding machine that I designed for seniors with Parkinson's disease. I would like to start my presentation by watching a video of a senior with Parkinson's disease. As you can see in the video, her hands are shaking when she is eating. However, since she is stubborn, she wants to be able to eat herself. I got inspired to do this project because my grandpa from both my mom's side and my dad's side has been experiencing something similar. Both of them have Parkinson's disease, just like the old lady in the video. They have a tremor in their hands when they are eating. From observation, they need a caretaker to feed them, or else they will spill the food on the table. I wish to solve this problem so that I could help my grandpa and people like them, so that they could eat independently with the aid of my machine. The next step that I took was to do research on the background of this problem. To begin with, Parkinson's disease is a disorder of the central nervous system that affects movement, often including tremors. It negatively affects patients and their family physically, psychologically, socially, and economically. 8.4% of adult citizens aged 30 to 64 in the United States have Parkinson's disease. This causes difficulties eating since the muscles in Parkinson's patients' jaw and face are inefficient. According to interviews with my grandpa and other seniors, the main food source for seniors is often semi-liquid food, since it's easier to digest and chew. After researching, I realized that the most existing designs are costly and complicated. Like this multi-user feeding robot, a lot of other designs are hard to install, like this vision-based assistive robot arm for people with severe disabilities. So I came up with 4 criteria for my design. First of all, it should be easy to install in nursery or home. Secondly, it should require minimized training or no training at all for users to use it. Thirdly, it should be cheap so that it will aid the patients and their family economically. Finally, and most importantly, it should be able to feed the target audience liquid food. In order to create this, I used 4 different tools. The first one is CAD. CAD stands for Computer-Aided Design. I used a website-based 3D modeling software called Onshape to draw out the design and test if it works periodically. The second one was Laser Cutter. I exported DFX drawings from Onshape to Illustrator. I printed them out using a laser cutter. I used both laser cut acrylic and wood in my design. The third one is 3D printer. I exported the STL file from Onshape and exported to a 3D printing software. Then I send the G-code file to the 3D printers and print them out. The last step was to assemble all the manufactured parts, such as laser-cutted parts and 3D printed parts, with off-the-shelf parts, like screws and axles, according to my CAD design. As is shown in the table, I came up with 4 feasible design ideas, including a weighted spoon, a bowl with opening, a mechanical arm, and a bowl with a spoon inside. I analyzed them based on the criteria that I came up, which includes easy to install, cheap, require minimized training, and most importantly, able to feed successfully. According to this table, the last 2 designs meet most criteria. I want to take a closer look to all my feasible design ideas and share my thought process on this feeding machine. First of all, I eliminated the design that failed to meet the criteria of being able to feed the patients. After this, I started working on 2 design ideas left and see if everything would work as what I was expecting. I started with the mechanical arm, but eliminated it later because it's relatively hard to design, time-consuming, and very similar to a lot of previous designs. I went back to keep on prototyping and advancing the design of a bowl with an opening. And here are my 4 versions for the design of a bowl with opening and my development process. The first version has a rectangular tube at the end of the cone-shaped container that have a cutting plate in the middle. However, the food cannot flow without spilling. For the second version, the cutting plate changed from rectangular to circular with opening on it. The tube of the container changed as well. I also designed the motion parts for this version. The third version is developed based on the second version. I increased the space between the two wheels and refined details based on the arrows of the second version. The fourth version is developed based on the third version. I did not have a chance to make it out yet, but I designed a spoon and the Geneva gear on the end so that for every 90 degree of the rotation of the wheel, the spoon will rotate once. And here are some parts of my final design. First of all, the container is cone-shaped so that the food will flow to the bottom of it. It is integrated with the top and bottom plates. The opening on the container are used for wheels to cut food. They're connected to the spoon at the bottom. Secondly, the cutting wheels. They're essential to my design since they're going to measure the same amount of food every single time. They're made out of laser-cut acrylic pieces, and they're twisted so that they're not identical, which will create 3 different stages when they're cutting food. Thirdly, the gears are used to change the motion from vertical to horizontal. They're 3D printed, and I extended the right one so that there will be more space for integration. Fourthly, the supports. There are 4 supports on the 4 corners of the plate to keep the plates in place. They'll also help with rotating the wheels and keep everything in place. Fifthly, the handle. They're essential because the user are going to rotate them to rotate the wheels. Along with the gears, it will change the motion from horizontal to vertical. In the future, I'm going to change it to a bigger handle so it's going to help Parkinson's patients to exercise. Sixthly, the spoon. It's very essential because it's used to serve food. 70% of the volume of the spoon is the volume of the food between the two wheels. It is integrated at the end of the tube of the container. Lastly, the Geneva gear. By using these gears, the spoon will be able to rotate 90 degrees for every rotation of the handle. I'll talk more about it in the next slide. This is an animation from a Geneva gear generator. It is 2-wheel system including a drive wheel, the dark blue one, and the Geneva wheel, the light blue one. As shown in the animation, when the drive wheel is rotating, the Geneva gear is not going to move until most of the time. It will move 90 degrees for every 1 rotation of the drive wheel. In my design, the drive wheel is going to be integrated with the cutting plates, and the spoon is going to be integrated with the Geneva gear. For test cases, I only had time to try 2 of them. The first one was raw rice, and the feeding machine worked very well for it. The machine is able to measure the same amount of rice every single time when the wheels rotate. The second one was water. It did not work well because the machine is not waterproof, so the water was leaking out of the machine. Here are 2 videos of the demonstration. The first one is an animation in CAD, and the second one is with my product that I created. As the handle rotates, the gears will rotate and the wheels will rotate with the gear. For the When the tube of the container reaches the opening of the first wheel, the food will be loaded between the 2 wheels. As the wheels keep rotating, the food will be located in the enclosed area between the wheels and eventually leave the tube to the spoon. And as you can see in the end of this video, the rice is on the spoon. I actually encountered a lot of problems and challenges when I was designing this. The first one that I encountered was the 3D printed parts are larger than how I designed them in CAD. What I did is I used a caliper to measure the clearance of each piece. Then I calculated the average clearance and changed my CAD based on that. The second problem was that the rotation of the wheel was not smooth. It stuck and could hardly turn sometimes. To solve this, I added standouts to make sure the wooden pieces are in place. The third and last problem was the spoon will move when the gear is moving. This makes integrating the spoon to the right place very hard. The solution I came up with was using the Geneva gear. And here's my conclusion and future opportunities. In version 1.5, I wish to turn feeding into exercise by changing the handle design so that when the user is rotating the handle, they will be able to get the exercise they need as a treatment for Parkinson's disease. In version 2.0, I wish to try different type of food and modify the design based on the performance of the machine when handling different food. I'll also make the system waterproof by adding rubber on the sides of the tube and making the wheels thinner. I would also like to bring the design to my grandpa and other target audiences so that it can actually help testing my machine and also helping them. On top of this, I will try to make my design available online. I'll publish the 2D drawings and 3D CAD to make a cheap feeding machine available for more people. I will also take it to nursery and people like my grandpa so that it will actually help seniors with Parkinson's disease. For people who are interested in taking research next year, I will encourage you to choose a topic that you're interested in because you're going to work on the same topic for a whole year. Additionally, never procrastinate. There are deadlines for paperwork. However, you're in charge of setting deadlines for yourself for your research. Time flies fast if you fail to manage your time wisely, and you might not be able to collect all the data you need. At the end of this presentation, I would like to acknowledge everyone who helped me in this research project. I would like to thank all my friends and Dr. Chen for giving me critical feedback about my design, my presentation, and my paper. It would not be possible for me to complete this project without Dr. Chen's advice. I would also like to thank Mr. Kwan. Although he's not physically present when I'm making this, all the Zoom meetings helped me a lot with the designing process. He inspired me to design the feeding machine the way it is. I would also like to thank my families for inspiring me and giving me advice, especially my grandpa. And thank you everyone for coming here and through Zoom. Here's my references.